Thank you for giving us the opportunity to describe to you our new weapon system testers. What we see here is a 132 SQB BTP unit in a travel road case with a weapons simulator and some storage lockers to hold cables, test components, and wiring assemblies. This tester is used to test weapons or ordnances using all the safety elements that you would have in a SQB tester, but all the features you would have in a DVM. So we can measure voltages, we can measure diode, we can measure several ranges of resistance. New features are being added every day. In the future, we will also have cable ID, so assemblies can be set up and connected properly and verified by the equipment. We're also adding bit, so we can do power-up testing and reading of serial bit patterns from your equipment and identify whether the equipment is good or bad based on that built-in test function. The tester uses all the safety features that we've incorporated into all of our SQB and NAV testers over the years. So we have fail-safe assemblies, which limit the current out to your weapon by built-in tamper-proofed assemblies. So these are potted, these are also sealed, and they're right on the exit point of the tester. So consequently, no wires internally can get chafed and short on the other side of these. They're right out here on the outside of the tester. We also have a manual feature. The manual feature, this cluster of buttons and this connector, allows you to verify a test that may have failed during the automated test by manually checking it. In this way, you don't need to buy a second portable piece of equipment to do that manual test. It's built into our functions. We have a display on the top which would show you the resistance range, the resistance being measured, information about the battery if it's a portable unit. That's all displayed on the upper portion. The lower portion identifies which test channels are being activated. Actually, which test points are being activated. Our system has a slight different nomenclature than you might be used to. Test channels is the way our previous systems work, and every channel was a makeup of 4 test wires, Kelvin, going out to your test load. We use a new approach now which use test points. Every test point can connect to a pin on your assembly with 2 wires. Those 2 wires can be positive or negative depending upon what they're connected to inside the tester. 2 other wires will come out and go to another pin. With our matrix mechanism, any pin can be tested to any other pin for resistance, voltage, diode functionality. Now the assembly that you see here, we're providing a tester, we're providing the cable set, and we're providing a weapons simulator. The concept of a weapons simulator is to give you a component that you can verify the system is running properly by measuring that component. That component emulates the loads that are in your weapon. You run that as the first test at the beginning of the day. It passes. Now you bring your cables and you start hooking up your weapon system. This allows you to validate everything, including your cables. Normally you would of course use cables long enough to attach to your actual weapon. We're using it in a portable fashion. The simulator, the weapon simulator, can be made in 2 different formats. It can be made as a rack attachment, which allows it to be placed in the same rack as the tester, or if you have a limited amount of circuit paths, it can be made as a plug arrangement. This can be mounted to the end of the cable that attaches to your weapon, and it protects the end of the cable and gives us loads that emulate the weapon. When you go to do the weapon, you simply unscrew it and bring the cable out and attach it to your weapon. So there are 2 formats, a plug format and a rack mount format. The connectors on the system are keyed, and in the future they will have cable ID resistors in them. Each one will have a unique resistor, so the tester can verify that that unique connector with its unique resistor is plugged into the proper fail-safe path. They're keyed, I slide them in and connect it up. Now I'm going to connect the simulator side. It's the same thing, it's keyed. These are a little more difficult because they're very small. You need to have little delicate fingers to get in there. And then lastly, we also have a feature for self-test. If you don't, or if you do have this tester, we still have a verification plug. This plug is mounted into the manual location. And during automatic tests, prior to every test sequence, it takes readings off of this. That serves two purposes. One is to verify that the channels are functioning properly, and the second is to get the zero at the thermal that you're exposing the system to. If I bring this and I test it here in a controlled environment, I'm going to have, say, 68 degrees. If I bring this out on the tarmac, I could be down as low as 40 degrees. This will compensate for that thermal and manage that data. So we always have that plugged in for automated testing. One more note for automated testing. When we run automated, we lock out these manual functions. And the reason why we do that is because we don't want an operator, while this is automatically running a test, changing a range in the middle of a test and giving you bad data. So I'm going to turn on the system. Oh. Click them all. Basically what I did was turned on our power supply, turned on my weapons simulator, and turned on my tester. The tester does a self-test. For a second, you're going to see a screen that shows you the version number of the software, the calibration date that the unit was last calibrated, and the layout of the system, how many test points it's capable of measuring. If you want to read that information in that 1 second, you really don't have a whole lot of time. If you power it down and power it back up with the select button held, that information now will display for about 10 seconds, and you can actually read it and check the version number of your software. These systems are all version controlled. We keep very tight control of the electrical and the mechanical designs of these so that they're consistent, and every time you purchase it, if you purchase the same model number, you get the same thing. We also control the calibration digitally. Unlike some testers where you have pots and adjustments, you have to open the unit to tweak. These aren't, they're full digital. With a calibration kit, you can actually do calibrations in the field with this system. And since it's digital, that's one of the reasons why we also store in it, in digital form, the calibration date. So when you're interfacing this with software, we know when this unit was calibrated. So we can stop a test if the unit is out of calibration, protecting your integrity of your data. In the back, we control the power coming into the system. The system is AC powered. That AC power supply has a minimum of 3 layers of barriers between it and the measurement test circuits. Those barriers protect against overvoltage, and they give ground isolation at each layer. That guarantees that at our measurement system, that measurement circuitry is floating relative to earth ground. The reason why we do that is we want to eliminate the risk of potential current paths from earth ground through the SQB payload and potential detonations of the target test circuits. We also want to control any other power sources that might come into the system. So to protect against a computer failure or a computer source of power, we connect between the computer and the unit through a fiber optic connection. This is a military-grade IP65 washdown fiber optic cable that, when connected, there's no way that electrical power from the computer can get to the tester. Now, these systems also come in 2 configurations at the time of purchase. This system, you can see when you're looking at it from the front, we have our exit paths to your UUT mounted on the front of the chassis. If you look at the back, you can see the notch. When you order it, we can arrange it so those come out the back. so that you can run those through the back of your rack instead of out the front. It depends on your particular tastes and your arrangement of your test lab. Now this system is made portable for demonstration purposes. It's not really, it's a transportable system, which would be fine. You can purchase it in this arrangement in a road case. But if you wanted it to be actually out in the field, there is another flavor of this which allows it to run in the field and hit those temperature ranges and still functions that you may have out in a Humvee out on the grounds. The system can be run in a rack with a rack mount computer. It can be run in the field or on a portable scenario with a tablet or a ruggedized laptop. We like this particular company because we can buy this hardware with or without any of the technology that often causes problem in classified environments. We can buy these without cameras, we can buy these with Wi-Fi, Bluetooth removed, not disabled, but removed. That allows us to bring these into classified environments where the rules about having those transmitters are disallowed. The other thing, of course, is in ordnance testing, none of us really want transmitters anywhere near where we're working. They have the possibility of interfering with circuitry and inadvertently triggering devices. I will hook this laptop up so we can see it running a sequence, and I'll describe how our software works and the way you can integrate this with your own software. So let's talk about software and integration for a moment. We provide or we sell software that will run the system. That software allows you as an engineer to define almost everything about a test sequence that you are performing or your operators are performing. You can also integrate this software into the system into your own software by using our app DLL or our low-level communication DLL. Both of those are written in C#. Or you can interface it directly through the serial port and use the serial command structure to communicate with the meter. So any one of those application methods allows you to communicate with the meter and shed as much of the software development as you might desire. We'll show you demonstrations with our software. So this software allows you to, as an engineer, define the sequence. It's a CSV file. The CSV file has its own command structure and it's defined for you, so it's very easy to use. The commands include defining whether it's going to be an automated test or a manual test. The manual tests are used with our PTU units. The automated tests are used with the SQB units. You can also define whether what circuits are being tested. You can define the name of the circuit, the two test point wires you're connecting to, the type of test, whether it's voltage, diode, or resistance, the range of the test, whether it's a 100 millivolt or 2 volt voltage test, or whether it's a 20 ohm to 2 meg resistance test. You can also define the pass-fail criteria for that test. First of all, you can define the type of pass-fail. So is it a test that I'm just collecting data? That's test type 1. Is it a test that the engineers are collecting data? We're testing against tolerances, but it is not a quality test and doesn't stop the weapon from being qualified to move on to the next delivery stage. Or is it a quality test where it must pass this test, and if it doesn't pass, the weapon is not past its quality test and doesn't move to the next stage of delivery. Those are all defined in that file. The type of pass-fail that's being done is also defined. Are we defining the minimum and maximum range that it must be within, or are we defining whether it's a tolerance and nominal arrangement? So nominal value plus or minus a tolerance value. That's configurable in the software. When you configure the sequence, they get stored onto the computer. When the operator goes to run a test, I'll run a new test, and this is a touch screen, so it should work. it comes up and allows me to go to this screen. I can select the tests that are available. Our engineers have made 2 test sequences for us to do for a demonstration. One is a very quick test. It only does the voltage and diode tests, and one is a full-up resistance test. I'll do the full-up resistance test. We also are set up so that we can interface with scanners. Come over on this side so we can see it better. I'm going to scan the weapons test simulator's serial number by moving this out of the way and scanning it. It automatically goes to the next line. It's looking for me to scan the operator ID. I'll take my ID off, scan it, and it automatically loads that data. So now that information is going to go in my computer and it's going to be stored with my test. It's automatically highlighted the OK button, so I really only have to hit continue. It's now loaded the sequence, and it's going to start by making sure I've got everything connected. So I'm checking to see, do I have this shorting plug? This is that self-test I talked about for thermal compensation. Enter, it runs down the test. This self-test happens for every range of the piece of equipment. So the diode range, 20 ohm to 2 meg, and 100 millivolt and 2 volt. Once it runs that, it'll ask me to make sure the ordnance or weapon is connected to the tester. Now, the first one of the day, we would plug it into our verification box to verify that the equipment is working. From then on, we'd connect it to the weapon. These prompts are completely controlled by you. So everything that you see here for text is in a rich edit text file that you as an engineer can change to define exactly the instructions you want your operator to follow. So you can mimic your test procedure as closely as possible here to help clarity and understanding of your operators. I've basically got all of them connected, all of them wired, and I'll hit enter to continue. If this system had the cable ID function, this is where it would do that verification measurement of each cable's resistance to validate whether it's correct. In this case, we don't have that function, so we've moved on to doing measurements. On the measurement screen, we see the unit or the range that the tester is being measured in, the value that's been measured, whether that value is presently passing or failing, whether it's internal, external circuit path, and what test points are A and B. The test point A is the positive side. For resistance tests, that's not important. But for voltage tests and diode tests, it is important. We also show the calibration date and how many days out of cal you are. This is taking the calibration information from the tester. This will show green if you're comfortably within cal. If you're within 30 days, it will turn yellow, warning you that you're about to go out of cal. And when you do go out of cal, it turns red and will not allow you to run measurements. The unit will not accept data that isn't with a cal meter. Middle section are the instructions that you see the operators receiving. It tells him what circuit's being tested. It tells him what 2 points are being probed on what connector. That also can be controlled by you, and more detail or less detail can be provided for your operators. In the bottom section, you see a list of the tests as they go. On the right, you can see that they're green on the right, telling you that they are passing. If anything fails, it will go red. Just above that, you see that the status of the part is pending. Hasn't finished all the tests, so I can't tell you if it's a pass or a fail part. Also, it tells you how many tests have been run, whether they've been passed, warning, or failed tests, and the counts associated with each one. Passing test is anything that was a test that was checked for verification or just measured. It says it passed. Any test that is out of tolerance but is not a QA test, will be a warning. And any test that is out of tolerance and is a QA test, it gets marked as a failed. Once it's completed, it'll indicate whether all pass, all failed. If any one failed, you'll have that information in the CSV file that's exported at the end of the test as well as on the report. The time you see it taking readings is adjustable. We can configure that. We've specifically configured it so that we have some time to talk about how the system is working. So it's got a couple of seconds of data stability and a couple of seconds of data reading. When working with standard circuits that don't have capacitance, you can bring these times down to a second each. With anything that has capacitance, though, you have to keep in mind that you have to wait for the circuit to stabilize as it charges on the test current. While it's running, let's talk about fail-safe and test currents. We design our systems with a 10 milliamp fail-safe design. That means internally, if everything goes wrong and the maximum voltage DC in the tester is available at the fail-safe input, then the fail-safe path resistors will limit that to no more than 10 milliamps maximum. That's called the fail-safe current. We also have a test current. Test current goes down with the range of measurement. So in the case of 20 ohm, the test current is about 2.5 milliamps. In the case of 20 meg, it's about 2 microamps. So the test current varies. The fail-safe current and the test current is the same for the automated test point paths as well as the manual path. These testers, for safety reasons, also have tamper-proof labels on the back. What we are protecting against is somebody opening up the tester and trying to fix something in it and inadvertently compromising the safety. For example, these modules have to be replaced with Space Electronics fail-safe modules. If somebody just put a connector there and took out all those internal parts inside that potted assembly, this unit would not meet the 10 milliamp safety rating. And it's not something that you want anybody to ever do. So these can always be sent back to Space Electronics for service. We're very reasonable and we're very timely. Calibration, if you don't buy a calibration kit, needs to be done annually. You can send it back to Space Electronics and we can perform that calibration with our equipment. Now that the test is complete, it indicates right away whether the vehicle or the unit under test passed or failed. This one has passed. So we're just going to say continue. This is for the operator to know if he needs to put some kind of an ID sticker or a hold tag if it's failed. He sees this prompt and he acts on it. This software is automatically set up to save the CSV file at the end of every test. So you always have a history of what tests have been done. So this is the CSV file that gets outputted automatically from our system. It goes into a results folder, which can be interrogated through a network device if this is in a rack and tied to the network, or it can be copied from this onto a thumb drive and put onto a computer where you can store it and analyze it. Basically shows information about when the test was done, what was tested, what was the calibration date of the equipment that was used, what was the serial number of the equipment that was used, and then the tests themselves. In development at Space Electronics is a ruggedized, roadworthy version of this tester. What that system will be the connectors themselves, a battery power system, with no displays or manual mode in a enclosure that is washdown rated, that will go out in the field and be rated for the full temperature range and environmental exposure that you would get in the field. Those systems will require ruggedized laptops for interfacing and running the equipment. This will give you something that you can drop in the back of a truck and drive out, with your ordnance system, and you can test it prior to launch to have confidence that the equipment is ready to do its task.